Okay, and we're back. So you've just finished up working on the fossil correlation lab. We're going to go to the next topic in geologic history. We're going to finish geologic history out by talking about how to find an exact age of rock. So the focus today will be on radioactive decay. You want to have page 1 of your reference tables open as well. I want to make sure that you realize that as we're talking, we are focusing on this top left chart. So what is radioactive decay? Well, a lot of us think of radioactivity as being something very dangerous, and it can be in certain instances, especially if you're talking about something like a nuclear power plant using uranium. And the decay process gives off radiation, which in effect does have the ability to denature our proteins and affect our DNA and potentially cause diseases and even death. So for our purpose, though, we are going to dial that back a little bit. We're not talking about the full-on nuclear fission of material. We're purely talking about the natural decay, the natural reduction in radiation of known sources on Earth to help us determine the age of rock. Right? One thing I would like to point out about radioactive decay, it's almost like a perfect clock if you're trying to figure out the age of something in the past. Because radioactive decay happens at a specific amount, and that specific amount of time is always going to be the same for our samples. So let's take a look here. We've got something that we need to learn called half-life. That is the amount of time, life, okay, the amount of time it takes for half of a material's radioactivity to decay. Okay, so half-life is the amount of time half of the radioactive material needs to decay. Okay? And this time factor for different materials has a certain number of time, or amount of time. So it's very predictable. Okay? This kind of is just giving you an illustration that we might have 100% of something that's radioactive, and eventually over time you have the amount of time related to when half of it is gone and almost all of it is gone. Key, you'll never get to zero. Okay? There's never going to be zero amount of radioactivity left, but it will get so small over time that maybe eventually certain elements are not as useful or accurate for dating rock layers. Okay? So here, as we decay, or as radioactive material breaks down into decay material, we have what's called a decay product. And that is stable, it's no longer radioactive. And that material will increase. So using the ratio between radioactive material left and the amount of decay product that has increased, we can determine an age of rock fossils, or the Earth for that matter. Okay. So if we take a look here, I've broken it down. This looks awfully complicated. Let me run through it rather quickly and make it a bit easier for you to comprehend or to digest. So we've got number of half-lives. So here we start at 0. 100% radioactive material right there. So we're at 0 half-lives. 100% material, all radioactive. Our first half-life, which in this case we don't know the amount of time yet, we're just purely talking in number of half-lives. So we go 1 half-life, we lose 50% of that radioactive material of the original number, or the original amount, and we gain 50% of that over in the decay product. Okay? So we're saying half of radioactive material is left from the original. If we go from 1 half-life to the second half-life, again, we don't know the amount of time yet, but it's the same amount of time. So from 0 to 1 and from 1 to 2, the amount of time is the same. Right? So we go from 1 half-life to 2 half-lives. We lose half of the radioactivity that was originally left in the sample. So we're going to go from 50 to 25% radioactive. We're going to gain that lost 25 is going to go over to the 75. So in a way, it's like we are losing 25 here, but it's being gained over here. So what we lose is then gained to the decay product. Again, you can see this ratio where there's a certain amount of either radioactive or decay that can indicate to us at what half-life or stage of half-life is that material. we can continue the trend, and that trend continues, where we take half of what is left in the next half-life, the third one, and we gain that other half over here in decay product. And that will continue until the numbers get so small or negligible that we're not really able to make much sense because it is already too close to zero. As we can see, the amount of fraction of decreased radioactive amount from the original whole, okay? So if we were to say that this was 1 gram, this is like saying there's a half a gram of radioactivity left in the sample. Then a quarter of a gram, an eighth of a gram, a 16th and a 32nd of a gram is left, okay? So let's come down here and try to show this thing as a graph. So here we are purely showing the number of half-lives. We're showing the percent remaining. We're not giving it an amount of mass yet, okay? But I have at least given you an example of mass over here on the right column. So we've got 0, 1, 2, 3, 4, 5 half-lives, very similar to last example. And we've got the percent remaining. I just want to show you that this line starts to flatten out, become slightly asymptotal to the 0 line on this graph, because as we go, we lose half of what's remaining. So the numbers I showed you up here, the numbers I showed you here, this is the predictable decay of radioactive material that's being lost. And what's being lost is going to be gained. So as it's being lost, it's being gained here. So let's see if I can get both of these sort of on the same screen at the same time. And I can show you that here we have 100% radioactive material. Down here we have 0 decay product. We move out 1 half-life and we see that we've lost 50% and we've gained 50%, being that we've lost radioactive and we've gained decay, stable decay product. We continue that process where we lose another 25 of radioactive, we gain that, and now we have 75% decay product. Now what eventually happens is that we start to assign time with a half-life. So if we're saying that this is 1 half-life, in this example I'm going to continue the process of introducing to you how this actually works. This is time, meaning 1 times 10 to the 9 years. That, if you were to add all the zeros, would be 1 billion years. So we're saying the half-life of this radioactive substance is 1 billion years. Let's rephrase that in another way. So I'm saying that if I am a material of radioactive nature and I decay and I lose half of my radioactivity and I lose that in 1 billion years, that means that in order for my radioactivity after that first half-life to decrease again by half, I have to go another 1 billion years. So you can see that even though this graph looks identical, we are now assigning time to these values instead of just purely saying it's a half-life. Right? And we're doing the same down here for decay. So the nature of the curve stays very similar. But what is assigned to the amount of time, or at what time you find your half-life, right? So if you were looking for that half-life, you find that first place where it hits 50%, and you can find that your half-life in this case is 1 billion years. Okay. There is a few very special elements that we like to use, one of them being carbon-14. Carbon-14 is a radioactive version of carbon, and it decays into nitrogen-14. So that's the decay product. So when we find a ratio of those two elements, we can determine the age of a fossil or a rock layer. And we do that oftentimes with many things in our current nature. So things that are current as in like less than 50,000 years. So once you hit this 50,000 years into the past, carbon-14 has broken down so much so that it's not really useful anymore. Okay? Other big thing, has to be organic. Okay? We are carbon-based life forms on this planet. Everything that was once living had carbon associated with it. So therefore, we can only use carbon-14 dating on previously organic material. Okay? We tend to use this to date back into our Pleistocene and our Holocene epochs, which are the two most recent ones. Okay? We sometimes are looking at things like mastodons, mammoths, maybe whales, anything else, even humans. So you may, in the past, you may see news reports where they pull this old and decayed but very well preserved person locked up in ice from maybe a few thousand years ago, as they unfortunately met their demise while traversing through a mountain pass, and maybe they got stuck in a snowstorm and they were buried under all this snow, and eventually they succumbed to their icy grave. We can use carbon-14 to date almost back to what we believe is the day of their death, which is amazing in itself. But to say the very least, we are using carbon-14 to say this person died 3,000 years ago, or this person died 4,205 years ago. We are using that ratio of carbon to nitrogen to figure that out. So let me, before we go too far into these examples below and questions to get us before we do some independent practice, I'd like to introduce you to page 1 of the reference tables again, but in this case we are in the top left corner of the reference tables. So we have radioactive decay data. Okay, this is the actual data we need to analyze rock layer ages. We've got radioactive isotope, the one I was just speaking to, carbon-14, potassium-40, uranium-238, and rubidium-87. Each of them have their elemental radioactive state. Okay? We have their stable decay product. So I don't mind if on here, your reference tables, you write radioactive here, and then you write decay. We're going to abbreviate it, PROD period for product, so that you can refer back to this and remind yourselves as you look at these things. We've got radioactive material here, we've got the decay product here. Then we've got the half-life time. This is the clock. So we've got for carbon-14, the clock for every half-life is 5,700 years. Otherwise known as in scientific notation, 5.7 times 10 to the third years. Remember that trick. Exponent, if you're multiplying, and it's a positive exponent, move your decimal to the right that number of times to get your value. We jump up rather precipitously when we take a look at potassium, uranium, and rubidium. We jump really high when it comes to the exponents. So we're dealing with billions of years here, billions of here, tens of billions of years here. Right? That's a 10 for the exponent. We haven't even been through the half-life yet on this planet. Anyways, so we've got 5,700 years, 1,300,000,000, 4,500,000,000. I would like to point out from when we were doing geologic history, and I made you add that little note to the bottom of page 8 of your reference tables, Earth's age, for proving its age of 4.6 billion years, we use the ratio of uranium to lead on this planet to determine that our Earth has almost just barely gone through one half-life of uranium decaying to stable lead. Okay? So keep that in mind here. Now, if you'd like to annotate this, you can. I'm going to tell you what the names of these other elemental symbols are, because not all of these symbols can be found at the bottom of page 16 for your elemental symbols. So here we've got carbon, nitrogen, potassium, which is why it's named potassium. Ar is argon. Ca you can find in your reference tables in the back. U is for uranium. Pb is lead. You can find that in your reference tables. Rb, rubidium. Sr, strontium. Okay? So each of these is the clock. So we're going to try using some of these to help us with our practice questions on the next page. By the way, if you haven't, throw a couple annotations over here now that you've been introduced to carbon-14 and how it works. All right, so here we've got 4 empty circles and we've got some questions. Okay, so let's start to analyze what's going on here by reading this first question. It says, how long will it take to reach the second circle if the half-life is 10 years? We've got a lot of blank circles. We've got information about a half-life, but how about we try to show this representative in a way where it makes sense what we're talking about. So I'm going to color in these circles as if they're going through their half-lives. And the color means that's radioactive. Okay? All right, so what we can see here is I have completely something full here. I have half, a quarter, and then I have an eighth of what's left. So here, I'm going to put my percentage. And you know what, this is a good practice to get into, is creating these particular diagrams, maybe not circles and shading every time, but getting in a habit of showing how the percentages change in radioactivity and how each of those jumps represents a half-life, and that half-life is usually defined to you either by the value in the question or by telling you what element you need to use from the reference tables. So let's fill this thing out a little bit, and I'll quit talking for a moment. I'll define HL. By the way, when I do these things here, I'll let you know, as I always do, whether you can do something like that on the Regents. No, you cannot abbreviate HL for half-life. You will have to write half-life out. But for our notes, this is a way for us to maybe abbreviate and get through it a little quicker. I'm going to add an arrow just in case we got to go any further. I'll deal with that later. So now, it says how long will it take to reach the second circle if the half-life is 10 years? So from here to here, if this is one half-life, this is a warm-up question. If it takes 10 years for one half-life, and this is one half-life, and this is the second circle, we're going to say that it takes 10 years. So not a trick question, just warming you up, okay? So then it says, how long will it take to reach the fourth circle? So this is the first, the second, the third, the fourth. We've got one half-life, 10 years. Two half-lives plus 10 years. Three half-lives to our fourth circle. That's plus another 10 years. So we've got 10 plus 10 plus 10. So we've got 30 years. Okay. What percentage of radioactive material is left after 20 years? So we've got 10 years per half-life, 10 one half-life, 20 total years, which is another 10-year jump of half-life. We are to here, and we see we have 25% remaining. How many years will it take until there's 6.25% of the original radioactive material left? Do we have 6.25 left up here? No. We have to solve for that. So we are going to go one more step out, which I don't have a whole lot of room, but you can see that if we were to divide 12.5, we should get a 6.25% in our next circle, and I don't know if I can do a half of an eighth, which is a 16th, but that's not too shabby. So we've got a 16th, and it's going to be one half-life, two half-lives, three half-lives, four half-lives. Is that the answer? No. No, but we do know we need to use four half-lives. We know how many years are in a half-life. So we know there are 10 years in a half-life. So we can solve that from here to here to here to here, there are 40 years that are necessary to go out to 6.25% remaining. Okay. So right now what I'd like you to try to do is I'd like you to try to apply this to an actual element being carbon-14 using the half-life of 5,700 years, also known as 5.7 times 10 to the 3 years. Okay? So take a moment, try to solve those questions, pause the video, give it a shot, we'll come back. Okay, so hopefully you've paused the video, you've given us a chance to actually do this. There's no harm, remember there's no shame in trying something out and then checking afterwards. It's trying, and if you're making mistakes, trying to learn from those mistakes. That's the process of learning. Remember kids, I can't download this into your heads. Alright, so we've got same setup. Just start mimicking what you've got. The tools, this is a tool that we're doing, or that we're using to do this. I realize that this is usually almost always the case for percentages. It's all about trying to figure out the amount in between for half-lives and how much time it takes to get to each of those half-lives. So we've got here, how long will it take to reach the second circle using carbon-14's half-life? We're in the same situation like the last one. So from here to here, that's 1 half-life. We know that it's 5,700 years for 1 half-life. So get to the second circle, we are going to say it is 5,700 years. Okay? Then it says what percentage of radioactive material is present after 11,400 years? Well, you've got to figure out how many half-lives go into 11,400 years. So you know you're dealing with 2 half-lives. That's half the answer. So we have to figure out the percentage at the second half-life. So this is 1 half-life, 2 half-lives. So this is the second half-life here. Okay? We have 25%. Lastly, how many years will it take until there are 6.25%? So if you really needed to, you've got to go out 1 more half-life to 6.25% again. So we've got 1, 2, 3, 4 half-lives. This time though, instead of 10 years, we're using 5,700 years. So if you do that math quick, you should end up with 22,000. Woo, board's acting up. 22,800 years. Okay. Now that you've got some of this here to back you up before you go into independent practice, I would like you to flip the page. And if you are in the packet that you have from class, we will eventually transition to just me communicating for you to open up a document within the Google folder. But you should be on the assignment, radioactive dating, guiding, and independent practice, question 1. So take a moment, read through question 1, and then we will come back and continue how to solve it. Go ahead and pause if you haven't already. Okay, hopefully you paused. As silly as this feels, doing the pause stop if you're not even bothering to pause the video. Alright, anyways, let's get back into the question. We've got Figure 1, base your answer to this question on the diagrams below and on your knowledge of earth science, your infinite knowledge of earth science. Alright, so the diagrams represent a model of the disintegration of a sample of radioactive isotope carbon-14, so C14. That means you better get into your reference tables. Alright, so we've got the original sample, we've got after 1 half-life. We've got a key here, that's key, okay? That's solid ones. Okay? So we've got refer to figure 1 and answer the following question. Boom, figure 1. So identify the radioactive isotope that has a half-life that is approximately the same as the estimated age of Earth. Ooh, let's read that again. That's a bit dense. So identify the radioactive isotope that has a half-life that is approximately the same as the estimated age of Earth by using the radioactive decay table of Earth science reference tables. Wow, this question, in this case, they gave you this image here, but it doesn't look like you're going to actually need it this time. Bit of a bait and switch. So that's why it's important to read through everything and determine what is most useful to you. So if we were to remember which radioactive element is used to help find the age of Earth, it's the one here that I'd like you to annotate. Okay. So let's come back here. Let's just make sure. Yep, we are analyzing which half-life is used for the age of Earth, and that is uranium. Okay? But what is important is that this is probably a diagram in your Regents exam that probably had a couple of questions lined up afterwards that required you to actually use this image. Okay? I like to throw those zingers in there a little bit just to keep you focused. All right, let's go to the next one. Take a moment for you to read through this one and to annotate. Had to make sure I was still recording. All right, so pause the video, take this one on. I'll be back literally in a jiffy. We're back. All right, so base your answer to the question on the graph below and your infinite knowledge of earth science. The graph shows the number of radioactive isotope X atoms. So we don't know what the isotope is yet. We don't know if it's carbon. We don't know if it's rubidium. We don't know if it's uranium. We don't know if it's potassium. We don't know. May not need to know. All right, so present as a sample of the isotope undergoes radioactive decay. So I've got radioactive decay as my title. I've got some axis titles. I've got time, hours. Oh, if we're dealing with hours, we're not dealing with years. We are not dealing with something from the reference tables yet. Not yet. Okay, number of radioactive atoms present. Okay, so we've got the amount of radioactivity, so the amount of atoms, the number of atoms, kind of like mass in a way. Okay? Based on this graph, the half-life of this radioactive isotope is, well, if we go back to those practice graphs that we had on the previous pages in our notes, we'll realize that all we need to do is find where we have 50% radioactive material left. So even though this isn't percentages, we do have 1,000 atoms. So if we were to think if half of the 1,000 atoms disappears from being radioactive, we're going to be down here at 500. So 500 is going to be what we want to see as the amount left after one half-life. Now, it's as easy peasy as going out to your graph and finding where it hits the data line. Come on down here, and you find out that 3 hours is the half-life for this radioactive material. So, with this overview of radioactive decay, I bid you to go back, check your notes, use the practice that we did in the notes, check out your reference tables, use the independent practice to kind of guide yourself through some more of these, check out the answer key, use the access points that you can find labeled in the Google Shared folder. If you have any questions, feel free to leave a comment below the video or hit me up in Google Classroom.